Good morning. I am a student of BSc Chemistry Honours second year. Today we will discuss the chapter of Organic Chemistry. The name of the chapter is Diazonium salts. So let's start the chapter. Diazonium salts, discovered by Peter Grace in 1858, constitute a very important class of aromatic compounds having the general formula ArN2 positive X negative, where X negative may be an anion such as chlorine negative, bromine negative, HSO4 negative, etc. The name diazonium itself originated from the fact that these compounds contain two nitrogen atoms, French azoate, that is equal to nitrogen, and resemble ammonium salts in certain respects. It may be pointed out that aliphatic diazonium salts, that is the compounds having the N2 positive X negative group attached to an alkyl radical, are too unstable to be isolated. Structure of diazonium salts. The simplest and most important diazonium salt is benzene diazonium chloride. Let us first consider the structure of this compound as a representative of the structures of diazonium salts in general. The important evidence leading to its structure may be summed as follows. First point, molecular formula. Its molecular formula is C6H5N2Cl. Second point, observed behavior. It is a colorless crystalline solid soluble in water but insoluble in organic solvents such as alcohol and ether. It undergoes ionization in aqueous solution as shown by the conductivity measurements of the solution. Thus, benzene diazonium chloride exhibits salt-like behavior. It undergoes many substitution reactions in which N2Cl group is replaced by monovalent groups such as halogens, cyanide, etc. It undergoes coupling reaction to form azo compounds such as para-hydroxyazobenzene. On reduction with stannous chloride and hydrochloric acid, it is reduced to phenyl hydrazine C6H5NH2. In alkaline solution, it forms salts known as diazotates, which exhibit geometrical isomerism and exist in syn or cis and anti or trans forms. Earlier formulae. Grace formula. The earliest structured formula for benzene diazonium chloride was suggested by its discoverer Peter Grace. In the formula, the two nitrogen atoms were directly attached to benzene nucleus as shown below. However, the formula was immediately rejected as it couldn't account for the following properties of benzene diazonium chloride. Its salt-like behavior, its reduction to phenyl hydrazine, which contains only one nitrogen directly attached to the benzene nucleus, the displacement of N2Cl group as a whole in most of the reactions, the formation of azo compounds in coupling reactions. Kekulé formula. Kekulé proposed the following structure in which only one nitrogen is directly attached to the benzene ring. This formula could explain most of the reactions of benzene diazonium chloride, but it failed to account for salt-like behavior of benzene diazonium chloride, instability of benzene diazonium chloride as compared to azo compounds since both contain nitrogen double bond linkage. Bloom-Strand formula and its modified form. Bloom-Strand suggested the following structure for benzene diazonium chloride. The structure has now been modified as benzene attached to nitrogen positive to chlorine negative. Supporting evidence. The above ionic character structure, which is comparable to that of ammonium chloride, is supported by following observations. Benzene diazonium chloride is soluble in water but not in organic solvents due to its salt-like structure. The conductivity of aqueous solution confirms the presence of charged structures. IR spectrum shows the presence of nitrogen-nitrogen triple bond. It can explain all the reactions of benzene diazonium chloride. It can explain the existence of geometric isomers of diazotates. It has been suggested that in presence of hydroxide ion, the diazonium ion exists in equilibrium with diazohydroxide, an unionized compound, and the salts derived from it are shown below. The concentration of the different species depends on the pH of the solution. In acid solutions, the equilibria favor the diazonium ion, while in alkaline solution, the equilibria are in favor of azotate. The diazotates can naturally exhibit geometrical isomerism and exist in syn or anti form as depicted below. Nomenclature of diazonium salts. Diazonium salts are named by attaching the word diazonium to the name of the parent aromatic compound. This is followed by the name of the anion, for example, benzene diazonium chloride, para-nitrobenzene diazonium hydrogen sulfate, para-toluene diazonium bromide, and para-chlorobenzene diazonium fluoborate. Preparation of diazonium salts, diazotization. Diazonium salts are usually prepared by reaction between aromatic primary amines and nitrous acid. The reaction is called diazotization and may be represented as procedure for diazotization. For carrying out diazotization, the amine is dissolved in an aqueous solution of the mineral acid and the resulting solution is cooled to about 273 Kelvin. A well-cooled aqueous solution of sodium nitrite is then added slowly, taking care that the temperature of reaction mixture does not rise above 278 to 283 Kelvin temperature. If the temperature is allowed to rise higher, the diazonium salt formed gets converted into phenol. The addition of sodium nitrite solution is stopped as soon as a few drops of the reaction mixture give a blue color with starch potassium iodide paper, indicating the presence of some unreacted nitrous acid in the reaction mixture. In other words, it shows the completion of diazotization. Since excess nitrous acid is likely to interfere with the subsequent reactions of diazonium salts, it is destroyed by adding a small quantity of urea. Any urea left unreacted does not interfere with the reaction of diazonium salts. The above solution containing the diazonium salt is used as such for the other reactions and no attempt is made to isolate the pure salt. This is because dry diazonium salts often undergo explosive spontaneous decomposition. Furthermore, since diazonium salts decompose slowly even in cold solution, the solution must be used for further reactions immediately after preparation. It may be pointed out the liberation of nitrous acid from sodium nitrite and the formation of diazonium salts requires 2 moles of mineral acid per mole of amine to be diazotized. But in actual practice, the amount of acid used in about 3 moles. The use of excess acid is necessary to maintain proper acidity for the reaction and to prevent the combination of diazonium salt with the diazotized amine. Precautions to be taken. During the preparation of diazonium salts, the following precautions should be taken. The temperature must be carefully controlled and not allowed to rise above 283 Kelvin, otherwise a phenol would be obtained. The mineral acid should be used in excess, otherwise diazonium salt formed would combine with diazotized amine. Excess of nitrous acid must be destroyed. Never try to prepare pure dry salt because it is highly unstable and undergo explosive decomposition. Mechanism of diazotization. It has been shown by Larberthy that the actual mechanism of diazotization depends upon the extent of acidity and the concentration of reactants. But there is no doubt that the nucleophilic amine undergoes attack by some electrophilic species, such as nitrosonium ion NO positive or nitrous anhydride N2O3 obtained from nitrous acid. Thus, one of the probable mechanisms which appear to operate in many cases may be summed up as follows. In the presence of strong acid, nitrous acid dissociates to give nitrosonium ion. The ion attacks the nitrogen of the amine to form an unstable N-nitroso-ammonium ion intermediate. The intermediate immediately loses a proton to form an N-nitrosoamide. This in turn undergoes a rearrangement by a proton shift similar to ketoenol tautomerism to form diazohydroxide. Finally, in the presence of acid, the diazohydroxide loses water to form the diazonium ion. The complete mechanism is as follows. Aromatic amines carrying electron withdrawing substituent such as NO2 on the ring are rather difficult to diazotize. This is because the electron withdrawing substituent reduces the nucleophilic character of nitrogen of the amine and thus renders it less susceptible to attack by electrophilic species. This observation also constitutes evidence in favor of the above mechanism. Diazonium salts containing anions such as BF4 negative are generally obtained from more common diazonium salts as shown below. The reaction of benzene diazonium chloride and fluoboric acid gives us benzene diazonium fluoborate plus HCl. Physical properties of diazonium salts. Diazonium salts are generally colorless crystalline solids freely soluble in water. They are seldom isolated because of their instability and explosive nature. With certain metallic salts such as zinc chloride, diazonium salts form double salts which are quite stable. Chemical properties of diazonium salts. Diazonium salts are highly reactive compounds and are extremely useful as intermediates in the preparation of many aromatic compounds. By the use of diazonium salts as intermediates, it is possible to introduce onto the aromatic ring substituents which are difficult to impossible to introduce by other methods. In addition, it is also possible to introduce substituents in position not favored otherwise in direct process. The reaction of diazonium salts may be divided into two main types. These are reaction in which N2 is given out and diazonium group is replaced by some other atom or group. Coupling reaction in which the nitrogen atoms are retained in the product. As already stated, diazonium salts are employed in various reactions in the form of their aqueous solutions, which are prepared just before they are required to be used. The important reactions of diazonium salts are discussed below. Reaction in which nitrogen is lost as N2 and the diazonium group is replaced by some other atom or group. The first reaction is replacement by ClBr or Cn. Sandmeyer reaction. A very important reaction of diazonium salts is the Sandmeyer reaction, in which the diazonium group is replaced by a chlorine or bromine atom or a cyanide group. The reaction is carried out by treating solution of freshly prepared diazonium salts with cuprous chloride, bromide or cyanide. Thus we have the following reactions. In case of replacement by cyanide, the diazonium salt solution is neutralized with sodium carbonate before being treated with cuprous cyanide. This is to prevent the loss of cyanide as HCN. Mechanism. The mechanism of Sandmeyer reaction is uncertain. However, a probable mechanism involving free radicals may be summed up as follows by considering the reaction with cuprous chloride. It appears that species such as CuCl2 negative, CuBr2 negative and CuCN whole twice negative are first formed which subsequently lose an electron to diazonium ion to yield an aryl radical, cupric salt and nitrogen. The aryl radical and cupric salt ultimately react to give the final product. Gattermann reaction. In a modified procedure known as Gattermann reaction, the replacement by ClBr or Cn is carried out by using copper powder and halogen acid or potassium cyanide in place of cuprous cyanide. That is the reactions. Synthesis utility. Sandmeyer or Getterman reaction offers a very useful method of preparing aryl chlorides and bromides in pure form. The method is preferred to direct halogenation as the latter usually results in the formation of mixture of products. Since the cyanides obtained by the above process can be easily hydrolyzed to carboxylic acid, this constitutes a good method for preparing aromatic acids. For example, orthotolvic acid. Orthotolvic acid may be prepared from toluene as follows. Replacement by iodine. Replacement of diazonium group by iodine can be brought about merely by warming the diazonium salt solution with potassium iodide solution. Mechanism of the reaction. The reaction proceeds by SN2 mechanism and constitutes the best method for introducing iodine onto the aromatic ring. Replacement by fluorine Wahl-Schiemann reaction. For replacing the diazonium group by fluorine, the diazonium salt solution is treated with fluoboric acid HbF4. When diazonium fluoborate gets precipitated, the precipitate is filtered, washed and dried to isolate the fluoborate. The dry salt on heating decomposes to yield the aryl fluoride, boron trifluoride and nitrogen. The reaction known as Wahl-Schiemann reaction may be depicted as follows. Mechanism of the reaction. The reactions proceed by SN1 mechanism as shown below. Replacement by OH. On warming the aqueous solution of the diazonium salt, the diazonium group is readily replaced by OH to yield a phenol. Mechanism. The reaction proceeds by SN1 mechanism as given below. The Aphoricene reaction takes place slowly even on allowing an ice-cold solution of diazonium salts to stand. That is why diazonium salt solutions are used for further reactions immediately after their preparation. The phenol formed in the reaction can couple with the diazonium salts to form azo compounds. The coupling reaction is, however, suppressed in strongly acidic solutions. As such, the formation of phenol is best carried out by slowly adding the diazonium salt solution to a large excess of boiling dilute sulfuric acid. Synthetic utility. The above method is very useful for preparing phenols which are otherwise difficult to obtain. For example, metabromophenol may be prepared from nitrobenzene as follows. Replacement by NO2 group. This is carried out by decomposing diazonium fluoborate with sodium nitrate solution in the presence of copper powder. Synthetic utility. The reaction can be used for introducing nitro group in specific positions in benzene ring. Replacement by aryl group. Gomberg-Bachmann reaction. Many diazonium salts react with other aromatic compounds in alkaline solution to furnish compound in which the diazonium group has been replaced by aryl group. Replacement by arsenic acid group. Bart reaction. This is carried out by decomposing a diazonium salt with sodium arsenide in the presence of a copper salt. Replacement on hydrogen. Replacement of diazonium group by hydrogen can be best carried out by allowing the diazonium salt solution to stand in contact with hypophosphorus acid, preferably in the presence of cuprous ions. The reaction may be represented as below. The reaction proceeds by a free radical mechanism as illustrated below. Synthetic utility of the reaction. This reaction affords a convenient method of removing an NH2 or NO2 group from an aromatic ring. The complete process involving diazotization of an amine and subsequent subsequent reduction of diazonium salt is called deamination. This can be very useful step in many synthesis. For example, for the synthesis of symmetric 1,3,5 tribromobenzene diazonium chloride reaction in which nitrogen atom are retained in the product. Reduction to hydrogens. No loss of nitrogen. On reduction with reducing agents such as stannous chloride and hydrochloric acid, sodium bisulfite or sodium sulfite, diazonium salts are reduced to hydrogens. Free hydrogen can be obtained from its salt by the reaction with sodium hydroxide. Coupling reaction. A very important group of reactions of diazonium salts involves the reaction of diazonium ions with aromatic compounds containing powerful electron releasing group such as OH, NH2, NHR and NR2. The reaction known as coupling leads to the reaction of compounds called azo compounds having the general formula this, where G is a substituent such as OH, NHR, NH2, NR2, etc. The azo compounds are strongly colored compounds which constitute a group of dyes known as azo dyes. The coupling reaction in general may be depicted as follows. It may be noted that the nitrogen of diazonium group is retained in the product and the action is generally takes place in para position with respect to the subsequent present on the aromatic ring being attacked. However, if the para position is already occupied, the attack occurs at ortho position. Mechanism of this reaction. The mechanism of coupling involves the usual electrophilic aromatic substitution in which the diazonium ion is the attacking reagent as shown below. It may be pointed out that the diazonium ion is very weakly electrophilic. That's why it can attack only very reactive aromatic rings, that is rings which contain strongly activated substituents. However, if the electrophilic character of diazonium ion is increased by introducing electron withdrawing substituents like NO2 into the aromatic ring of the diazonium ion, coupling may take place with even less reactive aromatic compounds. Choice of experimental conditions. An important factor to be taken care in coupling reaction is the choice of suitable experimental conditions. The reaction conditions should be such that coupling takes place rapidly and the possible side reactions are prevented from taking place. The most important reaction condition which requires to be regulated is the pH of the reaction medium. This is illustrated below in the case of coupling with phenols and tertiary amines. Coupling with phenols. When treated with phenol in weakly alkaline solution, diazonium salts undergo coupling to form hydroxyazo compounds. For example, this benzene diazonium chloride plus phenol in along the pH 9 to 10 gives para-hydroxyazobenzene. Mechanism. The mechanism of the reaction involves the electrophilic attack of diazonium ion on the phenoxide ion as shown below. Role of pH in the coupling reaction. The choice of optimum pH range to be employed in the reaction may be understood in the terms of the respective equilibria involving diazonium ion and phenoxide ion. It may be recalled that in presence of OH negative ion, the diazonium ion occurs in equilibrium with diazohydroxide and the diazotate salts. Both diazohydroxide and diazotates are not electrophilic and therefore do not take part in coupling. This means that in strongly alkaline reaction medium, that is high pH value, the concentration of attacking electrophilic species would be low. In other words, a high concentration of attacking reagent requires the solution to be acidic, that is low pH value. Phenol in aqueous solution occurs in equilibrium with phenoxide ion. Due to stronger electron releasing effect of O negative than OH, phenoxide ion is more reactive towards electrophilic attack, but the equilibrium depicted above would shift towards phenoxide ion only in an alkaline solution. Thus, a higher concentration of phenoxide ions requires the reaction medium to be alkaline, that is high pH value. In the light of above discussion, it is evident that the optimum pH range for the coupling reaction would be a result of compromise. The optimum pH range for coupling of phenol has been found to be 9 to 10. This means that coupling of phenol is best carried out in slightly alkaline medium. Coupling with tertiary amines. Coupling of diazonium salts with tertiary amines takes place in slightly acidic medium to form dialkyl amino-azo compounds. For example, benzene diazonium chloride plus N and dimethyl aniline along the pH 4 to 5 makes para-dimethyl aminobenzene. Mechanism. The mechanism of the reaction may be depicted as follows. You can see the reactions. Role of pH. As already explained, high concentration of diazonium ion requires the reaction medium to have a low pH value, but at low pH the amine will be largely protonated as shown below. Now the protonated amine due to positive charge is quietly unreactive towards electrophilic attack. This means that in coupling reaction the amine should be predominantly in the free form, which is possible only if the reaction medium has a high pH value. As a result of compromise between the pH range requirements of diazonium ion and the free amine, the actual pH range employed in the coupling of tertiary amines is 4 to 5. That is, the reaction medium is slightly acidic. Reaction with primary and secondary amines. Primary and secondary amines generally react with diazonium salts in mildly alkaline solution to form colorless diazoamino compounds. In this reaction, attack of diazonium ion takes place at amino nitrogen rather than on the ring. However, the diazoamino compound thus formed undergoes rearrangement when heated in acidic medium to form the colored azo compound. Here we can see an example. Synthetic applications of diazonium salts. In introducing the chemical behavior of diazonium salts, it was stated that diazonium salts can be employed as very useful intermediates in the synthesis of a number of aromatic compounds, many of which are difficult or impossible to synthesize by other methods. The preparation of orthotolvic acid, metabromophenol and 1,3,5-tribromobenzene were cited as some examples of the synthetic utility of diazonium salts. A few more examples are given below by way of further illustration. Synthesis of metabromotoluene from toluene. In the above synthesis of the conversion of this to this compound constitutes the key step. It is based on the fact that NHCOCH3 is much stronger ortho-para director than CH3 group. Since the para position is already blocked, bromine is introduced at ortho position with respect to NHCOCH3 or meta position with respect to CH3 group. Second one is the synthesis of para-bromobenzonitrile from nitrobenzene. Third is the reaction between for the synthesis of 3,4,5-triiodonitrobenzene from para-nitroaniline. If further required, the nitro compound may be remove its nitro group by conversion into NH2 group followed by diazotization and reduction to get 1,2,3-triiodobenzene. Synthesis of meta-dichlorobenzene from nitrobenzene is followed by nitrobenzene first reacted with Cl2 in the presence of FeCl3. It converts into metachloronitrobenzene. Then it undergoes partial reduction in the presence of SnHCl. It converts into metachloroaniline. Then under the reaction, this is diazotization reaction, and get reacted with CuCl, we get the product named as meta-dichlorobenzene. Synthesis of para-dinitrobenzene from aniline is as follows. You can see the all reaction. Here are some conversions. First conversion is about nitrobenzene into meta-nitrophenol. Second is about meta-nitroaniline into meta-chloroiodobenzene. And third one is para-toluidine into para-toluic acid. So let's do the first conversion, that is nitrobenzene into meta-nitrophenol. First, nitrobenzene is reacted with HNO3 in the presence of H2SO4, that is the nitration reaction, which gives 1,3-dinitrobenzene, which undergoes selective reduction in the presence of NH4SH. We get 1,3 nitroaniline in the presence, then perform the diazotization reaction and heat it in water. We get the product as metanitrophenol, which is the required product. Second conversion is metanitroaniline into metachloroiodobenzene. So metanitroaniline undergoes diazotization reaction. Then we can see in the NH2 group is converted into N2 positive Cl negative, and the nitro group remains as such. Then it gets reacted with CuCl. Then N2 positive Cl negative, that is diazonium group, is converted into chlorine group, and then it is get reacted with SnHCl, and it gives the product metachloroaniline that undergoes diazotization reaction and get reacted with Ki. We get the product as metachloroiodobenzene. Here our chapter gets end. Thank you.